Hello everyone, and welcome to another lecture in Computational Algebraic Geometry. So I promised you something about differential forms on curves. Let me now fulfill this promise and explain to you what are differential forms on curves, and afterwards we'll talk about how to integrate them. Now already that is the reason we're studying these differential forms. An integral requires two things. One of them is a domain, and one of them is a form. And when you integrate a form over a domain, you get a number. And in our case, we discussed what domains are on curves. The domain could be, of course, points or the curve itself, but what's interesting is that when the domain is a loop. So that was the previous lecture. Today we're going to discuss what we will be integrating over loops. And since loops are one-dimensional, we're going to be concentrating on the things that you would integrate on one-dimensional domains. So these would be one forms. So if you remember how integration works, in fact, you use the tangent directions in the domain and you feed these tangent directions into your form and you integrate something like a function. So form is something that eats tangent vectors and spits out functions if you want. So let's now then start with tangent directions, the thing that a form eats. So intuitively we know what tangent directions are. Usually we think of something embedded in an ambient space which we can visualize. So maybe this is in R3 now. I just drew a two-sphere in R3. And then I say, well, okay, at this point, there's a plane that's tangential to the surface. And the idea is that vectors in this tangent space are tangent vectors. So this is maybe what you learn in calculus. So, okay, so this intuition that you learn at the beginning of calculus has also a more intrinsic interpretation. And you say that a tangent vector at a point P on your manifold is something that differentiates functions. So what is a differentiation operator? It's something that is essentially that satisfies the Leibniz rule, but let's just stick to a function like this. So let's say I take some domain inside the complex numbers and I take a, well, for example, a holomorphic function. That's all I care. So I say that this differentiation with respect to the variable z of f. So this is a differentiation operator that takes any function and gives me a function. That's what we call the derivative of f. So this, in fact, this del over del z should be viewed as a collection of vectors because I can do this at every point. So this is a vector field. And the underlying vectors, say at a point P, would take a function and return the evaluation of the derivative of that function at P. So this is a vector. So if we were to go back to our picture, each of these arrows tells you in which direction you should differentiate f. So in the real picture, I can, for example, draw a path along my surface such that its tangent direction at this point is the vector of my choice. You restrict your function at that path, it becomes a single variable function, real variable, and then you differentiate it using one variable scenario. So that's how a vector gives you a differentiation operator. It turns out that the result is independent of the path you have chosen. It just has to be tangential to your vector. But we don't need to connect it to this intuition because I only care about this one-dimensional scenario. I only care about holomorphic functions and I only care about pretty much this differentiation. So the differentiation with respect to a complex variable. So some easy facts if you want. Well, since I didn't define a differentiation operator properly, so I'll just say that on the complex space, so every differentiation operator is just a constant scaling of the 1 by differentiation by z. And so you can put together all of these tangent spaces together. So the global sections of this tangent bundle, these are the holomorphic sections, which means an assignment of a tangent vector at each point. Since I've chosen a generator for each space here, so each of these TPCs is generated by this differentiation operator at P, so I can actually say that a global form will be a holomorphic function times del over del z. So this space is isomorphic to the space of holomorphic functions. And if you're interested in having sort of algebraic sections, then this would be, well, algebraic functions on the complex numbers, so rational functions with a pole at infinity. And of course, the same kind of result holds that if I were to restrict this to an open subset of the complex numbers, then the global sections of this tangent space will correspond to holomorphic functions on that open domain. This just allows me to describe, or I should say define, tangent vectors on a curve and talk about global sections of the tangent bundle. So I won't mention complex again in this setting. So a complex curve C, and by that I mean the complex points of C now. So this is a complex manifold. This is locally biholomorphic to disks inside the complex numbers. So that means around any point I can find a small Euclidean open neighborhood, which is biholomorphic to a small disk in the complex numbers. Notion of tangency is preserved by biholomorphism or diffeomorphism if you forget about holomorphic structure. So that if I understand differentiation on complex numbers, I understand differentiation on my complex curve. Well, that's the idea of having a manifold. So it's locally like these affine spaces. So if, for example, U in C is such that, so C is my curve, U is biholomorphic to some disk in here. So then we can write, and we typically do, write this biholomorphism with Z. So Z is then a coordinate function. And then once again, this del Z trivializes the tangent bundle at U. So what I should say is a section of this tangent bundle of C restricted to U. So if I were to say this in words, I'm saying that if I have a function in C, well, I restrict this function first to U, and I view this function as a function on a small disk in the complex numbers. So it's a function in Z, let's say. Then I differentiate this function with respect to this variable Z. That's my differentiation operator. And that's then my tangent vector field. And if we were to now interpret this result here, I'm saying that any other vector field on the curve or on a part of the curve containing U restricts to a holomorphic function times this differentiation operator. So let me write this down. Any vector field. So a vector field is just a collection of vectors at appropriate points. And such a thing will have to be of the form Gz times del over del Z, G holomorphic. Right, so this isn't very interesting since the C is like the complex numbers. Everything that I said here is just a statement about the complex numbers, what we just discussed above. So it becomes interesting, or almost it's about to become interesting, if we were to talk about global things on C. So whether or not I can patch together some local holomorphic fields to get something global on C. So it turns out that you cannot do this, and that's why we don't work with tangent vectors, but instead work with their duals. But let's make this statement precise. So once again, I'm using the notation TC to denote the tangent bundle of C. So you can view this as the union of these tangent planes at each point. I mean, obviously I have some kind of holomorphic structure here, so I can talk about holomorphic sections, but this local structure allows me to put them together and view this as a complex manifold. And I care about the global sections of this tangent bundle. so global holomorphic sections of TC, of the tangent bundle. So now, because C is compact, so I define the curve as something compact. Obviously, this is not necessarily. So for simplicity, I define the curve as something that's compact. So holomorphic sections on a curve, and an algebraic curve, will actually correspond to algebraic sections. So if you're thinking of this scheme theoretically, what you find will agree with what I'm talking about here. Now here's the reason why we don't really work with tangent bundles in this setup. So there are no global holomorphic sections of the tangent bundle. So there is no vector field on a smooth proper curve if the genus of the curve is at least 2. And this thing is one-dimensional if the genus is 1, and 3-dimensional if genus is 0. Okay, so there is something interesting happening here, but I'm losing access to pretty much all the curves there are. So what we'll see later is that if I work with a dual of the tangent bundle, then I get something interesting here. But let's deal with this fact first. I'm not going to prove it, but if you know some basic statements, I can tell you how to prove the statement. So you know TC is a line bundle. Well, obviously, so it's locally like a neighborhood U times C, so that's complex line, so it's a line bundle, and line bundles have degrees associated to them, and the degree is 2 minus 2g. So you can deduce this in several ways, but for example, Riemann row. And this is negative if g is greater than 1. And one interpretation of degree is that if you have a global section, the degree is its number of zeros. And, well, a holomorphic section cannot have poles. So when you have a negative number here, it means that you cannot have any holomorphic form, so any holomorphic section of TC. So that proves this 0 part. Well, TC is just trivial when G is 1. So one way to believe it is to say that an elliptic curve is actually a quotient of the complex numbers by a lattice. And the tangent directions here are invariant under translation. So the tangents, the constant tangent vector here descends to C. So genus equals 0 is T of P1. Well, this is a little bit easier because the degree completely classifies a line bundle on P1. So here when I plug in G equals 0, I have degree 2. So then this is isomorphic to this canonical line bundle, this twist. And its global sections are just forms of degree 2 in the homogeneous coordinates of P1. So that gives me this C3 here. Okay, with what I've said, you can only handle TP1 easily, and it's a good exercise to play around with this. So take two coordinates, one around 0 and one around infinity. So let Z be a coordinate around 0, so maybe 0, 1. And I'm going to take the obvious coordinate so that it covers, it's a well-defined coordinate everywhere except infinity. And let's say T is the coordinate around infinity, so that is 1, 0. And now I'm asking you to compare the vector field attained from Z with the vector field attained from T. So compare. And where can you compare them? On the locus where both vector fields are defined. So this is P1 minus 0 and infinity. So these 2 points. And what do I mean by compare? What we've talked about is already that this vector field will be a scalar of this vector field by a holomorphic function on this domain. So there is a function here which you can write in terms of t or z, such that the vector field corresponding to z is that function times the vector field corresponding to t. And how do you find this? Well, you use the chain formula. Remember, this is a differentiation operator, and so is this. And if I were to change variables from z to t, this is like applying the chain rule on differentiation. So as not to take the fun out of it, I'm not going to write the rest of it down. So that's your exercise. Okay, so after all this preparation with tangent vectors, so one forms are just duals to those things. So informally, so I'm going to say something is a one form if it's something that eats a vector or a vector field. And here, what does eat mean? Well, it's a function, so it takes a vector or a vector field and sort of returns or spits out a number. Or in the case that you have a vector field, so you have a collection of vectors, you're supposed to spit out a collection of numbers, hence a function. And such a thing is called, well, either a covector or a covector field, if it is a vector field, or sometimes called a one form. So if I were to define this star to denote dual of a vector space or a lattice or whatever, so in this case, let's say V is a vector space and I consider its dual, then the dual of a tangent space at a point, say of our curve, this will be the dual of the space will be the covectors at P, or one forms at P. Okay, so this is just language, and another notation that's used is, well, typically we write omega 1 of C, at least in algebraic geometry this is much more common. You write omega 1 of C to denote the dual tangent bundle. So the hom here is supposed to be the hom in terms of line bundles. So this is a line bundle, this is the trivial line bundle. Take the dual in that sense, or it's the union of these duals. And now what's going to be interesting for us are the space of global sections of this cotangent bundle. So this is the cotangent bundle. So as before, I write H0 for the global sections of this line bundle, of the cotangent bundle. So these would be the global holomorphic one forms on C. I will also talk about the local structure of the cotangent bundle, so it will be clear what I mean by this holomorphic forms, holomorphic sections of this cotangent bundle. But let's just grab the reason why we are interested with these cotangent bundles. So there's a theorem due to Riemann that says the dimension of this space is in fact the genus of the curve. So this is a complex vector space. So I mean this thing is a complex vector space as dimension G. So in that sense, this dual of the tangent bundle is much better than the tangent bundle itself. Okay, now let's do another local analysis of this cotangent bundle. So the complex curve locally looks like the complex plane. So I'm just going to talk about the complex numbers. Again, I'm working on C with coordinate function z. Then we said this differentiation operator is a global section of the tangent bundle. So I also said that the tangent bundle is trivial, so that the cotangent bundle is also trivial. And there's a corresponding dual covector bundle. So this thing has a dual, which we write dz. So the notation will become clear in just a second. And by dual, it means that if I pair these two things, so remember dz eats del over del z, so that if I make this pairing at each point, this is a function, and I'm saying that this function is constantly equal to 1. Now to justify this notation and explain basically the other sections, remember that this differentiation operator eats functions, but covectors also eats this. So functions are like dual to this, and these are also dual to this. So functions are going to give us differentials. So let f be a holomorphic function, so then this pairing with the function and the tangent vector field gives us the function f prime z. In other words, f behaves like f prime times dz. Since there's only one tangent vector really, so this thing generates the tangent bundle, the operation of this pairing is completely described by what f does to this object. So it does this, it returns f prime z, but so does f prime z times dz. That also has the same effect when paired with del over del z. And we write df for this object. Right, so this is also consistent with how you represent df in calculus. And if we're being honest, I didn't need a coordinate to define this pairing with vectors. And if you do it properly, then of course dz is just the pairing of the function z with this vector field. So hence this notation. Okay, so I've completely described all cotangent vectors and cotangent vector fields on the complex numbers. And in turn, this gives me a description of all cotangent fields on the curve locally. So I should say this gives a complete local description. So if I have a coordinate function, so if I choose an Euclidean open neighborhood with a coordinate function, then again dz is a cotangent vector field that trivializes the cotangent bundle. So I write the cotangent bundle restricted to U has this section dz that is non-zero. That's non-zero everywhere. And now we have the dual exercise. So with z and t equals 1 over z local functions at p1. So you should compare dz and dt. Maybe this is a little bit simpler now. So this exercise is actually a little simpler than the previous exercise, but it's dual, so you can get one from the other. And in doing so, show that the cotangent bundle has no global sections. So of course this is just the genus 0 case of Riemann's theorem. So the theorem over here, C when it's P1, this is 0, so this vector space is 0, which means the only section is the 0 section. And by no global sections, I mean no non-zero. And what you need here, so after you compare dz and dt, is that a function on C so is bounded if it vanishes at infinity, and hence constant. But if it vanishes at 0 and if it's constant, then it's 0. So this is what you need to use to prove, well, Riemann's theorem, if you want, at genus equals 0. All right, so that concludes our discussion for today. We had meant to explain Riemann's theorem, so the basic objects in Riemann's theorem, and we even proved the genus 0 case. And it's always a little bit annoying that tangent directions is much more intuitive in differential geometry and it's much more visual, but algebraic geometry works a little bit better with omega 1, so with these cotangent vectors. And here we see an example that on curves there are essentially no global tangent vector fields. So this was our theorem here, but if you use the cotangent bundle, then you have a lot of sections. Not only that, in the next lecture we're going to talk about how we can extract valuable information from this vector space. And this will allow us to represent a curve in a more transcendental way. So not with polynomial equations, but with periods. All right, I'll see you in the next lecture.